Our next application of nonlinear least squares is nonlinear model fitting. And so we'll just look at what happens when the parameters enter the model in a non-affine way. When they enter in an affine way, you have just linear least squares, and we already know how to do that. So nonlinear model fitting looks like this. We have our predictor, that's our model or predictor, f hat of xi, that is going to be the ith feature vector, and then the parameter theta, that's what we seek to choose. And then this is the prediction, so this is really y hat I, right? And this is the sum of the squares of the errors, prediction errors, right? So now the difference here is that we are not assuming that f hat depends in an affine way on theta. Now, in the linear and the parameters model, it looks like this, and this is the general case of what it would be if f hat was a linear function of theta. That's called the linear in parameters model because it's a linear function of the parameters. Of course, it's not necessarily a linear function of x, and usually is not, but it's a linear function of the parameters. So here we're going to allow this f hat to be a nonlinear function of the model parameters. And we'll see that there's lots of examples of where that can be helpful. It can also improve interpretability, things like that. And we're going to minimize over the model parameters theta. So we'll look at a quick example. So we have some data, and for some reason, we believe that it has the form of a decaying sinusoid. Okay, so we're going to write it this way. It's theta 1 times exp theta 2x. Theta 2 gives you the decay rate if it's negative, or positive, the growth rate. And then cosine term, cosine theta 3x plus theta 4. Theta 3 is essentially the frequency of the sinusoid, and theta 4 gives you the offset or phase for that. So that's a model that's parameterized by 4 parameters, and then your job is to, given some data points, which you can see on this plot are the little green circles. Given the data points, your job is to choose theta 1, theta 2, theta 3, theta 4 to fit, to get a good fit with your data. Now, that ends up with a nonlinear least squares problem because you end up with this objective. You sum over all of your data points. This thing, of course, that's y hat. That's y hat I, like that. And you can see that it doesn't, it's not linear. Well, actually, I should say one thing. It is linear in theta 1. So we could solve for theta 1 by a least squares problem, but not theta 2, theta 3, and theta 4. Okay, so this, I would say things like this are quite, this is easily done using Levenberg-Marquardt. And in fact, I believe the fit that we're showing there is one computed from these data points using Levenberg-Marquardt. And you can see it fits a decaying sinusoid like quite nicely. Okay. The next example of this is something called orthogonal distance regression. So let's remember that when you actually normally fit a function, what happens is you'd have a curve like this. That's your approximation, and you have a data point like this or like that, something like that. What we measure there is the vertical distance between your data point and the value of the model here. That's the traditional thing. If you look at traditional model fitting, you do that. You have it's the vertical distance between the data point and the function value. In some cases, you literally want to fit a curve, and if you're fitting a curve, not a function, I mean, if you think of it as a curve, not a function, then basically what it does is what you really should do is look at the actual distance to the curve. Now, the distance to the curve is defined as the closest point on the distance of the closest point on the curve to you, and so that means that instead of penalizing the vertical distance like this, we're actually, if the curve looks like that, we're actually going to penalize you for being away from the curve. So that's it. This would be as if, in this case, you're not really thinking of this as a function. You're thinking of it more as a relation or a curve. This picture shows you, how you would do that, what the picture is for that. And, it's similar to, but slightly different from it's slightly different from normal fitting. Actually, the main point here is that you're allowed, when you have a data point, you're allowed not to associate it with the same value of x. You're actually allowed to mess with the x and compare it to a slightly different one. So actually, sometimes people call this an error in the features model, because what we're giving ourselves license to do is to actually change the value of x associated with a data point. So that looks like this. So we'll write it out as a nonlinear least squares problem. What we'll do is we'll take the difference in the y's, but we're going to evaluate it at a ui. Ui is going to be a variable. Like I said, we don't actually, if you fit ui, if you insist ui equals xi, we're back where we were before. But what we're going to do is we're actually going to allow you to mess with that, and then we're actually going to penalize you for basically choosing an x an x value called ui, which is not the same as the given x value xi. And that if you look at this case in 1D, you kind of get the idea that the distance to the curve here is two things. It's the vertical distance, which we're kind of that's the one that's this term, right? And then there's this term, right? Here, u and x are scalars, so it's just the absolute value. So it's the square root of the sum of the squares, and the distance squared is the sum of the squares. So here, what we're going to do is we're going to optimize in this problem over the following variables: theta, those are the model parameters, and ui. So by the way, even in this case, if theta enters linearly into f hat, so it's a linear in the parameters model, even in this case, this is a nonlinear least squares problem because we also have the ui's there, which we're allowed to mess with. Okay, so that is this is called orthogonal distance regression. I guess it's called orthogonal because you associate with each point a point on the curve on the graph of the function, and the tangent to the function there is orthogonal to the deviation from that point to the given data point. So that's why it's called orthogonal distance regression. But you'll hear this and you'll see this in a bunch of applications. The next topic is nonlinear least squares classification. So let's see how this works. Well, recall that in a linear least squares classifier, what we do is first we fit by least squares an f tilde of x. That's simply a regression or a model prediction that predicts the real number that it should be ideally close to -1 or +1. That's the idea. Then, of course, we're not allowed, if someone says, for this feature vector, do you think it's true or false? You're not allowed to say it's 0.6 or something, or partly true or something like that. What you'll do instead is we'll take the sign of that. So that's the actual predictor. Okay, and we just use ordinary least squares to do this. Now, a nonlinear least squares classifier does this. It starts with the following observation. If we're going to work directly with the sign, right? In least squares classification, we don't use the sign at all. That's a post process, right? We simply use least squares, which we know how to do. We fit it, and then we take the sign. And actually, the weird part is it kind of works pretty well often. But okay, here we're going to take into account the fact that we're going to use the sign. So let's see how this works. Sine of f hat of xi has only two values, plus or minus 1. Yi has only two values, plus or minus 1. So if I subtract them, you either get 0 if they agree, or you get you either get +2 or -2. And those are the two cases when it doesn't agree. Now, when you square +2 or -2, you get 4. So it turns out the sum over the data of sine f tilde of xi minus yi squared is actually 4 times the number of errors. So now what we're going to do, we're going to directly, or not directly, not quite, we're going to attempt to minimize that because we really would like to pick parameters for which our model makes as few errors as possible. Okay, so let's try that. Oh, one minor problem. Sine of f tilde of x is discontinuous, and so it's not differentiable, right? Because the sine function, goes like this. It's got a jump at 0. In this case, it's where f tilde of x is 0. Actually, interestingly, it's got a jump. F tilde of x equals 0 is some people call that the confusion point, because in a classifier, f tilde of x equals 0 means, I don't know, it could be -1 or +1. F tilde equals 0.3 means, okay, I think f hat should be 1. Minus 0.3 means f hat should probably be -1. But 0 means like, I don't know. I don't know. So it's a decision. And at that confusion point, I should say, it's actually there's a big jump. It's non-differentiable. So what we do instead is you just simply replace sine with a differentiable approximation of it. For example, a sigmoid function, which I'll show you shortly. And then you just use Levenberg-Marquardt to minimize this. It's just fine. It's a non-linear least squares problem. Okay, so here's a sigmoid function. You'll probably see this in a whole bunch of different things, but that's it. And the idea is, here's the sine function, right? And the sigmoid function is like a smooth approximation of it. So that's the idea. So we just have a sigmoid function in there like that. And that's what we're going to do. Okay, so this actually works shockingly well. So we'll go back to the MNIST handwritten digit data set, the very, very famous data set these days, or not anymore because people have moved on to much bigger ones, like CFAR and stuff like that. Okay, so, but the feature vector here, x, is a 493 vector of pixel intensities, I think including one that's constant, right? So that's it. And we're going to make a nonlinear least squares 10-way multiclass classifier. So, when we do this, I mean, you get down to 7.5% error on this. So the Boolean classifiers are computed by solving this nonlinear least squares problem, right? Which says minimize this, and we take phi to be a sigmoid here. Here we have regularization, and sure enough, as lambda gets bigger, we actually improve on our test error, and so we should take lambda somewhere in this region right here, right? So we could take it to be, I don't know, 0.3, 0.5, I don't know, something like that, somewhere in that range. So that's how that works. Okay, we're going to take that same problem and we're going to do a little bit of feature engineering. We're going to do profoundly stupid feature engineering, which is we're going to generate 5,000 random features, which is you take random linear combinations, then you take the sign or something. No, sorry, positive part. Right, and that's just I mean, you could do way, way better if you sort of did handcrafted features, but this is just to show you what happens if you just do some feature engineering. The test set error, in this case, drops to 2%. By the way, that's the performance of human beings on recognizing digits. In other words, if you simply take those digits, show them to a person, and they're like, yeah, sure, you just say, usually this would be like an undergrad or something like that, and we'd force them to do it or something in a class. That'd be part of the class is you have to look at 300 digits and type in whether it's 0 to 9. That's it. When you do that, the test set error drop for people. They get an error rate that's about 2%. So about 1 in 50. And some of these things are written. These handwritten things are written pretty poorly, right? And sometimes you would look at it and you'd say that is a 7, but the data would say that's a 9, or at least that person thought they were writing a 9. It looks like a 7, but it's a 9. So, all right. So that means that just using pretty much the material of this book in class, you match human performance. It's actually really kind of a stunning thing to think about briefly, because if you think about like how dumb what's happening is, but you understand all the moving parts. It's just pixels. The algorithm you put together, which would be Levenberg-Marquardt on this thing, it's profoundly stupid. It does not know what integers are. It knows nothing. And yet here it is classifying digits just as well as people are. Now, if you do more feature engineering, you can easily beat human performance substantially, which starts getting weird and creepy if you think about it. I should also add that, with I mean, there's other methods. This is an ideal problem for these classifiers called neural networks, and they can easily get superhuman performance on these, like just easily. I should add that you can actually minimize, you can fit neural networks using Levenberg Marquardt. Anyway, so this shows you that just putting together some bits and pieces from this course, you actually get to maybe not the state of the art, but you're not too far behind, and at least it demystifies how all these things work. This is kind of how they all work. If you go and look at how these are actually done on your internships or whatever, you'll see that it's very similar to the stuff we've been talking about.